There are a number of techniques for solving quadratic equations, but none of these techniques is of any use if the quadratic has no real solutions. So the discriminant is a useful tool for testing if a quadratic has any solutions at all. In this video, we'll look at examples where we use the discriminant to determine if a quadratic has any real solutions. Let's start with an example. The area of this rectangle is modeled by this quadratic function, a equals x squared minus 3x minus 10. Determine the number of roots and acceptable values for x that result in a positive value for the area. If this quadratic can model the area of this rectangle, then it should be possible to write it as the product of two linear binomials, as shown here. But to do that, this quadratic needs to have at least one real root. Let's use the discriminant to determine the number of roots it does have. When calculating the discriminant, keep these rules in mind. If the discriminant is greater than 0, the quadratic has two real roots. If the discriminant is equal to 0, then the quadratic has only one real root, which means it's a perfect square. But if the discriminant has a value less than 0, then the quadratic has no real roots. Let's calculate the discriminant for our quadratic. The b value of -3 goes here. The a value of 1 goes here. And the c value of -10 goes here. Simplify the numerical expression over several steps. The result is a discriminant greater than 0, which means that there are two real roots. The graph of the quadratic shows the two real roots. However, the y values that have a positive value for the area are in this range, which corresponds to the values of x greater than 5. Let's look at another example. Can this quadratic function be used to model the area of a square? A equals x squared plus 30x plus 225. If so, what is the minimum allowable area for this function? As before, let's calculate the discriminant to find the number of real roots. Recall the three possible outcomes for the discriminant value and what these outcomes mean in terms of the number of roots. Let's calculate the discriminant for our quadratic. The b value of 30 goes here. The a value of 1 goes here. And the c value of 225 goes here. Simplify the numerical expression over several steps. The result is a discriminant of 0, which means that this quadratic function can be written as the square of a linear binomial. The minimum allowable area is when x is equal to 0, which results in an area of 225. This means that the minimum allowable area is 225, and the allowed x values are greater than 0. Let's look at a final example. How do you know that this function has no real roots? A equals the quantity x plus 2i times the quantity x minus 2i. How can you use the discriminant to show that it has no real roots? This function is written in factored form and has complex terms. In fact, the terms x plus 2i and x minus 2i are called complex conjugates and are the complex roots of a quadratic. In order to calculate the discriminant, we need to multiply these binomials to get a quadratic function in standard form. Here is the expansion. You'll see that the linear terms cancel each other out, and the I squared term becomes a -1. This simplifies to x squared plus 4. Now we can calculate the discriminant. There is no x term, so the b value is 0. The a term of 1 goes here. and the c value of 4 goes here. As you can see, the discriminant is a negative number, which means that the quadratic has complex roots. And as we saw from the original factored form of the quadratic, these are the complex roots.